So I'm going to finish up chapter 1, which was, I was doing the modern physics update, and then I will enter chapter 2. So last time I was talking about how the clever ideas of the ancient thinkers, we still see some of those clever methods today, okay, in some of the modern scientific discoveries. And I showed you some wonderful pictures of imaging atoms on a surface, atoms of iron on a surface. And here I'm going to show you a few more pictures. For example, here is a picture of a virus. That we can take a picture of its molecular structure nowadays with the tools that we have. And in fact, on the Cornell campus, we have some very powerful X-ray machines. The Cornell High Energy Electron Source is a very powerful X-ray machines that allow you to look closely into the structure of complex molecules like viruses. Okay, so if you have a virus and you look inside with the X-rays, just like you look for a cavity in your teeth with X-rays, well, these are much more powerful X-rays. They can actually tell the arrangement of the individual molecular structures inside, and it turns out that there's a lot of symmetry in many of these viruses as to how the molecules are arranged. These are not individual atoms, okay? These are individual molecules. And it turns out that in some of these molecules you find symmetries like the icosahedron of Pythagoras. Now, if you go deeper into the structure of matter, go deeper than the molecular structure, and you come to atoms, okay, you also notice that atoms themselves, of what we thought of atoms in the early days, are not actually simple, but that they have structure, they have internal structure. And there's symmetry in that internal structure. And if you go deeper and you go into, say, the nucleus of the atom, you've all heard about the nucleus, then the nucleus has structure, and it consists of protons and neutrons, which are arranged in some symmetrical ways. And the proton itself has structure, which consists of quarks, okay? And there also there's levels of symmetry. So as we go deeper and deeper into the structure of matter, you see more and more of the examples of symmetry in nature. I'm going to just show you a couple of these. So, you know, the periodic table that I mentioned earlier, it exists because there's symmetry in the structure of the atoms of the elements that make up the table, okay? And I will show you the symmetry in the atom of neon and the symmetry in the atom of chromium. I'll show you pictures of that right now. And later on, we will discuss what that symmetry means. So here's the symmetry that we have found in the atom of neon, okay? So this is the way the electron clouds distribute themselves around the nucleus of neon. And this is the symmetry in the atom of chromium. Okay, so you can see the picture that we have of the atom of chromium has internal beauty to it. Okay? And this is what I'm trying to stress upon you, is that in nature we try to understand the beauty and the symmetry and the mathematical patterns. Now these symmetries exist not only in the substances of nature, but also in the physical laws that we use to understand how things connect to each other. Okay? So there are different kinds of symmetries, and we will encounter mostly what I call special symmetries, because general symmetries are somewhat harder. And I'll give you examples of general symmetries, but we'll mostly talk about special symmetries. So special symmetries are what you've studied already in section, like mirror symmetry, or time reversal, and we'll talk about time reversal some more, or charge inversion for antiparticles. So we'll talk about that later when we discuss antiparticles. And then there are, and I'll give you more examples of these, okay? Then there are general symmetries called spatial translation, rotation, time translation, and I'm going to illustrate that with an example that you may have seen in high school, except that in high school, I bet you they don't discuss symmetry as much. You've all seen the swinging pendulum. And what I want to discuss over here is that the laws that govern the behavior of the swinging pendulum have built into that the behavior of the pendulum doesn't care about, if you were taking a movie of the pendulum and you started the movie at an arbitrary time, then the pendulum swing would look the same no matter what time you started to film the swinging of the pendulum. In fact, if somebody showed you a movie of the swinging pendulum, you wouldn't be able to tell what time that movie started. I mean, the movie could have started here, okay, or it could have actually started right there. As long as my hand is not in the picture and the pendulum is swinging freely and you're taking a movie of it, you cannot tell what time the swinging pendulum started. And this is called time translation symmetry. Right? Turns out that through very clever arguments, a woman physicist by the name of Emile Noether, later on in the 1900s, she showed that this time symmetry really means conservation of energy. Okay, so you've all heard of conservation of energy. You know, energy can convert from one form to another, and that really is an indirect consequence of the fact that the laws of nature are the same no matter how time flows. Similarly, the laws of nature are the same no matter where I run this pendulum. So I could run this pendulum here, or I could be walking around, okay, and the pendulum behavior would, the laws governing would be the same as long as I'm moving at a constant velocity. So these are called general symmetries, okay, and we won't talk too much about general symmetries. We'll talk more about special symmetries. Symmetries allow you to figure out what kind of behaviors are allowed and what kind of behaviors are forbidden. So for example, with energy conservation, you know you can prove that certain kinds of phenomenon cannot be possible because energy is not conserved. Okay? Similarly, momentum and angular momentum are other quantities which are related to these general symmetries, and we will not talk about too much. Symmetry also allows you to simplify the analysis of complex problems, and I'll do one with you as a quiz question here a little bit later on. All right, so let's talk about the more special symmetries that are easier to visualize, like mirror symmetry. Well, we know that if I put my hand in the mirror, right, this left hand kind of looks like a right hand, and so these two hands are not the same. They actually mirror reflections of each other. Okay, so my body has mirror symmetry to it, and it turns out that all molecular substances that exist in nature, like amino acids, have both the right hand, you know, they have a molecular structure which has a handedness to it. And the handedness can be either left-handedness or right-handedness, and both of these kind of structures can exist in nature. Well, as it turns out, that all living creatures are constructed out of one kind of amino acid, which is the left-hand amino acid. No right-hand amino acids available in living things. Right? So one might think that, oh, gee, the right-hand amino acid is not allowed by nature. That's not true. Nature allows a right-handed amino acid. I can construct one in the laboratory. Okay? And it'll have similar properties to the left-handed one, except for some differences. So for example, those people who have diabetes, you know, you take certain kinds of sugar, which are constructed with right-hand molecules, and when you absorb that, when you take that sugar, it tastes sweet, but it doesn't absorb, it's not absorbed by your body, you know, because it's the right-hand symmetry. And so that's the way you make sugar-free, one way to make sugar-free substances. All right, now let's talk about time reversal symmetry. And your question is going to be based on that. So, you know, when I throw a ball in the air in the form of a, in the form of a trajectory here, you see that it's a parabola. And that parabola can actually be constructed in a very nice way by using the symmetric, the laws of symmetry. So let me take this and demonstrate to you that the parabolic motion is really can be reconstructed from one half of that motion by doing mirror symmetry and time reversal symmetry. Okay, let me show you that. So what I'm going to do, I'm going to go to that wall, and I'm going to throw this ball in half the parabola against that wall. Unfortunately, that wall has bricks with cracks in it. Okay, so if my ball hits a crack, it's not going to come back exactly the way I threw it. Okay, so I'll have to do it again. So excuse that possibility. So I'm going to throw this ball against the wall, and then it comes back. Okay, in this one it came back. Okay, yeah. Any luck? All right, you're supposed to catch it, you know. So if I throw this ball in a certain trajectory, right, it comes back in a trajectory that is, now let me bring the picture back here for you. That would be normal. So if I throw the ball in this trajectory here, okay, it came back in this trajectory with the opposite arrow. Or if I were to reflect the motion of this ball in the mirror, now all of you are not going to be able to see this because this mirror is not very big, but maybe somebody over there can see, because I'm not going to throw the ball because it'll happen too fast. So I'm going to kind of guide the ball through the mirror, and you should look at the path of the ball in the mirror, okay? So look at the path of the ball in the mirror, and then some other guys. How many over there saw the path of the ball in the mirror? Okay, good. And now see the path of the ball in the mirror. So that's the mirror symmetric version. Okay, so that's the mirror's reflection of this path, okay? So here I'm throwing the ball up against a mirror, and here's what you're supposed to have seen, right? Now, what I did by throwing this ball against it and waiting for this ball to come back is what you might call, take this path and time reverse it, just like the ball came back, right? So if I take this mirror path and time reverse it, then I'll have this path. So when I combine these two, okay, I'll have this path, okay? So analyzing the parabolic path in nature is equivalent to making it up in terms of these two symmetries, which are these special symmetries that you see in nature. Okay, now, you see these special symmetries in nature a lot when you're up against a water fountain, okay, and you see these wonderful trajectories, and they have built into it time reversal and mirror symmetries. So now this is the first question, right? I'm going to, maybe it's too easy, maybe it's a little bit hard, but it's really two questions, okay? In case the first one is hard. What I'm going to do is I'm going to throw this ball straight up in the air, and you watch the motion of this ball. Is that right? And then the question relates to what would happen if I were to drop that ball from rest, okay? So you have to do two things now. You have to be an observer and carefully see what's happening to the ball in terms of observe the speed of the ball, okay? And then try to figure out which is the correct path or the correct trajectory of the ball when it's falling. Okay, ready? I'm not going to show you it falling, okay? All right, I'll do it again. I'm not going to show you it falling, okay? All right, I'll do it again. All right, so you observe the path going up, all right? What I want you to do is I want you to pick which of these pictures properly represents the position of the ball fall as it falls in equal intervals of time. Okay, so if these were, like, say, 1/10 of a second, these would be the positions of the ball every 1/10 of a second. In order for you to figure that out, you should have watched carefully what I did and now apply some symmetry principle to pick the right picture. Now we'll see what the answers are, and I won't tell you what the correct answer is, okay? Most of you chose A. Well, it looks like you've convinced yourself the right answer. But some of you, like 20, 30 of you, did not choose A. Maybe the A guys who chose A are wrong. Okay, I'm not going to tell you if it's right. I can set it later. So what I'm going to do is I'm going to give you another chance to think about it. Okay. So those who did it, now I'm going to actually draw the picture of the ball rising, right? And draw the important feature of that picture, okay, and ask you to answer the question again. Okay, let's see how many people felt convinced about their first answer, and the correct answer is, in fact, this answer. Oops, what happened here? A. All right, okay. So what I'm trying to show you here is the consequence of time reversal symmetry. Okay, so the ball going up, that picture I gave you, and you should have observed it, and the main point there is that at the top of the trajectory, the ball comes to rest. So when the ball starts from the top at rest, okay, then it's if you time reverse it. So now what do I mean by time reverse it? What I mean is take a movie of this flight, okay, then stop the movie here, and then play the movie backwards. If you play the movie backwards, it will look exactly like this, okay, except it'll look like the ball is falling down, but it's really a movie of the ball going up reversed. So the point is that the movie of a ball falling down is the same as the movie of a ball going up in time reversal. Okay? So when you apply time reversal symmetry to this picture, you should get this picture. This picture says that the speed of the ball does not change as it falls. This picture says that the ball is moving fast first, right, and then slowing down. And this picture said it's kind of it's speeding up and then slowing down. So all of these are wrong. This is the direct symmetric combination of that. So that's how we use symmetry to figure out what's going to happen in situations that we cannot observe. Okay. So far we discussed how reason is so successful, in figuring out how nature behaves, and we discussed how observation is so successful. So now I'm going to turn things around and show you how reason is a failure, okay, and how observation also can be a failure. Okay. All right. So we all know about Pythagoras' brilliant success in figuring out the shape of the earth and the shape of the universe, because he was guided by his higher mind, his inner mind, that the cosmos must be beautiful, and that beauty is reflected in its symmetry, and because of that he chose the earth to be a sphere. Now he went then much further. He said, if the heavens look the same in all directions, okay, the earth must be at the center of the heavens. Symmetry, right? We look all around, everything's the same, we are in the middle. So is that right or is that wrong? We all know, of course, it's wrong. But if I ask you, or if you can debate this among yourselves, how do you really know that the earth is not the center? It's actually quite involved. The time that we changed our thinking from the fact that the earth is the center of the cosmos to the sun is, that the earth is the center of the solar system, to the sun is the center of the system, there were an attempt to explain why certain observations were taking place. Okay? And some of them who know this, one of the most important observations was the retrograde motion of Mars. Okay? That was the most important observation that led the revolutionary scientist whose name was, anybody know the guy who first put forward the idea that no, the sun does not go around the earth goes around the sun? Copernicus, right. So that was the main idea that he was trying to understand. But there were many others. And we'll cover that when we come to motion in the heavens. But the point is that by using these symmetry principles, Pythagoras reached a false conclusion. Here's another false conclusion he reached. He said that the path of the heavenly bodies, the sun and the moon, must be beautiful. There must be perfect circles. Also wrong. Okay? Turned out the path of the heavenly bodies are not perfect circles. They're nearly perfect circles. They're actually ellipses. So these ideas about Pythagoras, and who Plato, by the way, really supported them very strongly, these ideas kept astronomy on the wrong path for 2,000 years. Okay? So reason cannot by itself be, the main way to move forward. All right, now let's look at some examples of observation. Again, we know that Aristotle was extremely successful in showing that the spherical shape of the earth through many different paths, through the ellipse and through the eclipse and so on. And his main point was that science needs empirical content. So now I'm going to show you how he used the empirical content to figure out the reason that objects move the way they do. Okay, objects means objects on earth and objects in the heaven move the way they do. And from these observations, Aristotle came to some really remarkable conclusion. So he said, observe the change and motion in the heavens. For example, he says the sun, you look at it every day, and it never changes. It looks the same every day, except for occasional solar eclipses, which we know happens because because the moon comes in between. So that's understood. The moon goes through a pattern of appearances through what we call a regular cycle of 1 month. So in 28 days, the moon goes through what we call the lunar phases. So at times it looks crescent, and at times it looks full, and so on. These are the crescent moons in the sunset and crescent moons in sunrise. And so the pattern of the moon repeats, in this pattern every month. Okay? So as a heavenly body, it has an unchanging cycle of shapes that it goes through. Again, except for lunar eclipses, which are also understood because the Earth gets in the way between the sun and the moon. All right. If you look at the stars, okay, every night you see the constellations, and they gave them names. You know, the Egyptians gave them names, the Babylonian gave them the same names or similar names, and the Greeks adopted these names, you know, like the bear and the kite and the snake and so on. And every night, those constellations look the same. You know, they don't change their shape or they don't move in a different direction. Every night the stars are the same, etc. So the stars look the same. They maintain their positions and their shape throughout all history. One question you might ask yourself is that true for the next 10,000 years, that the constellations will look the same? Okay? Ask yourself that question. So the conclusion that Aristotle reached is, I see that in the heavens, the nature of the bodies never change. In fact, the motion of objects in the heavens, like the planets and the moon, are all eternal circles. They just keep going on and on and on in eternal motion. Circular motion in the heavens does not come to a stop. It just goes on forever and ever. In fact, that's the name, that's how the word eternal came about. Okay? Eternal is the motion of ether. Okay? Eternal. So heavenly motion never changes. It needs no assistance. Okay? This is his conclusions. On the other hand, Earth is, by contrast, in complete flux. Okay? Everything is changing. Snow, if you look at snow, it's going to melt tomorrow. Okay? Wood will get all rotten, and iron will rust, and so on. And so nothing on Earth remains the same. People will, you know, get old, die, and decay, and so on. So the substance on heaven never changes, but the substance on Earth is always changing. Okay? So he reaches this conclusion that heaven and Earth are made of different stuff. Not only is the substance different, but also their motion is different. Okay? So notice, for example, that if a stone moves, there is a natural motion, namely the stone falls down. Okay? Stone is made out of earth, all right? Or water will fall down. Okay? And fire, he says, what does fire do? Well, fire's tendency is always to move up. Okay? Now, assuming that I don't set the fire alarm, all right, let me show you what Aristotle observed about fire. And I'm sure you all seen the fireplace, right? And in the fireplace, you notice that the flames are always rising, right? Yeah, the flames are rising. And in fact, if you try to force it, oops, I've got to do it again. If you try to force it down, right, let me try it on the other side, so I don't have this bend. If you try to force the fire down, then, okay, if you try to force the fire down, it wants to go up, right? It always wants to go up. So the natural motion of fire is up. So what about water? I'm sorry, what about air? Well, air you can't quite see which way it's going to move, right? But you can make air, the motion of air, quite visible. So here, I'm going to make air visible for you, right? So here's a beaker of water. I'm going to do a trivial thing that you've all done before. I'm going to make air appear, right? So that you can see it. Okay, everybody see the air rising? Okay, so air wants to go up. So these elements, earth, natural motion is down. Fire, natural motion is up. Okay, air, natural motion is up. Water, actually the natural motion of water is down. However, if you look at this picture of water, okay, the natural motion is down, but eventually the water kind of spreads out, all right, over the surface of the earth. Okay, so there you see water spreading out over the surface of the earth. Okay, I have a reason for doing this messy demonstration. Okay, now that's kind of nice for for vertical motion, up and down. Okay, up and down motion is natural motion for the elements. However, horizontal motion is not natural. Okay, this is all Aristotle's observations. Okay, horizontal motion is not natural. So if I start something in horizontal motion, what happens? What happens to this object in horizontal motion? Does it keep going forever and ever? No, it comes to a stop. Horizontal motion is not natural. It comes to a stop. It needs assistance to keep going. So if you're going to sail on the ocean, you're going to need a wind at your back to sail. So horizontal motion comes to a stop. In fact, circular motion on Earth is also not natural. Like in the heavens, circular motion is natural. The heavenly bodies are always going round and round, okay, without any assistance. Now, if I start some circular motion on Earth, right? If I start some circular motion on Earth, right, and then let it go. Oh, that wasn't very good. I'm supposed to try to let it go so it stays on the table. All right. So the circular motion becomes straight line motion, and then like a straight line motion, what's going to happen to it eventually? It's going to stop, right? So this is Aristotle's observations. So circular motion is not natural, it's going to stop. Okay. So what was his conclusion? Well, first conclusion was that since heaven and earth are made up of substances that behave differently, and they have laws that are different, like their motion is different, this means that heaven and earth are distinct regions. Okay? On earth, all the substances decay, and natural motion is only up or down. And the substance of heaven is different from the substance of earth. The substance of heaven is made out of ether, and the substance of earth is fire, air, water, and earth, changing all the time. Okay? And motion is different. So he comes to this conclusion. And he now invents a model. Now this is the most important part of his thinking. He says, I understand all of this motion. How can I understand all of these different kinds of motion? Why do these different substances of the universe move so differently? Why does it look like there's sort of chaos in this whole process? And as you know, if you have chaos, then you try to bring order into that chaos by thinking about it and trying to rearrange the natural occurrence of things to put them in order. And that's what Aristotle did. He said, I'm going to bring order into the cosmos. So what he said was, I'm going to invent a fundamental ordering principle. Just like when you do the Rubik's Cube, you must have some basic rules, that if I don't really know how to do a Rubik's Cube, but whoever does, that you have to have some rules, that you have to move in a certain way in order for some layer to be moving in one direction. But anyway, the fundamental rule that Aristotle came up with is that every element, earth, air, water, fire, etc., has a natural place in the universe. Okay? It has a natural place in the universe. And what is that natural place? Well, the element earth's natural place is at the center of the universe. Okay? And so earth is over here. And the natural place of water is the surface of the earth. You see, that's why the water kind of spreads out, because it wants to go to its natural place. Well, that comes later, okay? The first principle is, what is its natural place? Where is it always trying to go? It's always trying to go to the surface. Air its natural place of the air is another sphere above the sphere of earth and water, and that's called atmosphere. Okay? Your word atmosphere comes directly from Aristotle, okay? So you see, you still believe what Aristotle showed. And fire, the natural place of fire, is another sphere above that of air. Okay, so Aristotle's model, and then above the sphere of fire comes the sphere of ether, which is where the heavenly bodies are, and all the heavens are. Okay, so this model was pleasing because it had order, it took away all the chaos, and it explained it has a symmetry to it, just like Pythagoras' spherical symmetry, and it provided nice, simple, rational arguments for certain kinds of behavior. And you might think about it too, like why do we have volcanoes and so on. But one simple argument would be lightning. Why do we have lightning? Well, what happens when lightning strikes a tree? It catches fire. So lightning is fire, right? Now, what's happening is, when you see this atmosphere crack up, open up in cracks, then you can see the sphere of fire behind it. That's lightning. So that's a nice rational explanation. It replaced all of that Greek myths about God Zeus having this big thunderbolt in his hand, and if he didn't like somebody, he threw it at him, and that was lightning. Okay? So this is a very nice rational explanation for lightning. Now, you will see that the effort to bring order, where we see lots of different things happening, is among the first efforts that we do as scientists. Okay? So to give you a very dramatic example, this 19th century chemist, does anybody know his name? The guy who made the periodic table? What was his name? So Dmitry Mendeleev was the guy who took all the elements that he knew about. There were actually only 50 that he knew about. And he put them in this order, which we call the periodic table. We'll study why that's the way that he ordered it. So Aristotle's explanation accounted for a variety of motion. The objects move the way they do because they're all trying to get to their natural place. Okay? So Earth is trying to get to the center of the universe. And in our Earth, things are mixed up because of all the commotion and chaos. And everything is trying to go to its natural place. And so that's the nature of the motion that we observe as the elements seek that. So for example, if you have an object made of the element Earth, like this stone, then if I let it go, it wants to go to its natural place, which is the center of the Earth, right? In fact, if I throw it in the opposite direction, it will slow down. I couldn't see it. It'll slow down and turn around and go back to the center of the Earth, right? So that's a nice explanation of why the object slows down and turns around, because it always wants to go to the center of the Earth. So the property that Earth has that explains its motion is gravitas. Okay? In fact, the more Earth there is, the more gravitas there is, the heavier it is. Okay? And that's Aristotle's word, gravitas. So he coined the idea first of gravity. Okay? And of course, it's gone through many intellectual transformations since then, which we will follow. So gravity. Now, if you launch an object up, you will see that the motion will deteriorate and it'll come to a stop and then revert to natural motion. So Aristotle provided a nice explanation for a difficult puzzle. And that puzzle came about when Pythagoras and he proved that the Earth is a sphere. Okay? And the puzzle was, if the Earth is a sphere, what's happening to this guy? Right? And he said, look, if man of anything on Earth is made of Earth, right? All objects of Earth want to go to the center of the Earth, gravity, gravitas. Okay? And so there really is no difficulty. Okay? This guy is saying, I'm fine. Okay? We're all fine because we're all attracted to the center of the Earth and we're not going to fall off the Earth. So that was his idea. That was his successful idea that remained. Everything else thrown out. Okay? This is the only idea that remained from this picture. All right. So if we pause now and reflect a little bit on Aristotle's failures and successes, then you will see that even though we threw out all of Aristotle's ideas, his intellectual contribution was still very worthwhile. And what do I mean by his intellectual contribution? Well, he developed a model to organize elements and the motion. And then that model became the framework for all scientists who came after him to work with it. Right? And that's what we're always doing. But the periodic table is a model for how to organize the elements. That became the framework to come up with atoms. Okay? Then atoms were a model. In the beginning, Democritus said atoms cannot be divided any further. They cannot change. Well, that's all not true. Atoms can be divided further. One atom can change into another. All right? So you see, you work with a model, but the point is that you need to make this model based on observation and reason, and then that model can become the paradigm. Now, his design for the cosmos, by the way, was so attractive that it became what we call a paradigm. And many people have studied paradigm, especially in philosophy. And we humans tend to do this, at least with our brains. We come up with a certain explanation that is comprehensive, that explains things, and then we fall into this paradigm. Okay? I mean, there have been all kinds of false paradigms, like our ethnic makeup is going to influence where we're going to end up in society. These are all false paradigms. Okay, but these were paradigms at some point. Okay, and Aristotle had a paradigm. Now, what people did was, if they observed something that kind of didn't agree with the paradigm, for example, if they needed to explain something about the paradigm, like you saw that the falling body speeds up, right? From the distances between the objects, right? You saw that the body was speeding up. I can actually try to prove to you that as a body falls further and further, it's actually going to go faster. What I'm going to do, I'm going to put this little ping pong ball on top of this tennis ball. I'm going to drop it from here. And this is not one of these experiments that's always very successful. So I have to ask my excuses before I start. Okay, and I'm going to have just a small fall. And if this moves at a slow speed, it will kick the ping pong ball a certain distance. Okay, if it moves fast, it will kick the ping pong ball very high. Right. So let's go short. All right? Okay, let's go short. All right, now let's go higher. Okay, that wasn't good because it landed into me. So you couldn't see what happened, right? Let's do that again. All right? So that says that the speed here was higher. And now let's try the big fall, right? Okay, so just trying to prove that the further it falls, the faster it's going to be at the end, right? All right. So why does this falling body speed up? In other demonstrations, I used to have glass, and I used to crack the glass, and then the glass would fly all over the place. That became a little dangerous. All right. So the explanation was, within this paradigm, the explanation was that the closer the tennis ball approaches Earth, the more eager it is to get there. So it goes faster. Right? Nice explanation. All right. Another observation that was made, right? You could say, let's take a leaf and let's take a stone, right? And let's drop them. You see the stone is already on the ground and the leaf is already still in the air. Why is that? Why does the leaf fall slower than the stone? Well, you know why it is, but I'll give you Aristotle's an Aristotelian explanation. The explanation is that the stone is heavier than the leaf. It has more gravitas. And so it wants to return to the earth faster. So heavy objects will fall faster than light objects. Okay, that's the conclusion from the Aristotelian paradigm. Okay, and not only that, but once the paradigm took hold, then people began to twist observations that were obviously contradictory into the paradigm by making up clever explanations. So let me show you a contradiction now. We have an object here, which is let's say this object here, and it's falling down. So nice, it's made out of earth, right? But now, let me put this object down at the bottom of this beaker. You know what's going to happen, right? Maybe I will fail. Okay, now I got it down at the bottom of the beaker, okay? And let it go. Oops, it's going up. So now wait a minute now. Is this object made to fall down? Is this natural place in the center of the universe? Or is this natural place up? We have a contradiction. So let's modify the model to fit. This object is made partly of earth and partly of air. Right? So when it's falling through air, the earth part dominates and it falls down. But when it's falling through water, the air part dominates like the bubbles and it goes up. So it fits within the Aristotelian model. So that's what happens to a paradigm. Okay? Now, just to convince you that this kind of thing is already going on, I want to tell you that the most popularly accepted model for particles and atoms and all that today is called, it's given the name, standard model, the standard model. And everybody believes that it explains everything, well, most everything. And whenever we find a new phenomenon, a new reaction or something, well, we figure out how to how to interpret the behavior to fit it within the standard model. Okay? Because there are some revolutionaries that say, throw the standard model out. Okay, it's wrong. The universe looks completely different. Well, that's going on today. Okay? So this was Aristotle's standard model. Okay? And it was a paradigm. Okay, I explained that. So the progress in science depends on devising models, which Aristotle did. But the part that Aristotelians but didn't get to, okay, they didn't get to, was to challenge these models with tests, like I just did, okay, and try to understand those in their own right. So Aristotle's picture dominated European thought for 2,000 years, not only because he was Aristotle and so on, but because of other reasons, which you will see in chapters 3 and 4, the main being that his ideas got mixed up with religion. And so once they became incorporated with religion, you dare not contradict Aristotle, because Aristotle became sanctity, So that was, and we'll see that. So the idea of experimental tests to check the model seems extremely commonplace today, but it took a long time to form. Okay? It took 2,000 years to form after Aristotle. And Galileo was one of the major breakthroughs in that. And we'll see that in chapter 3 and 4. So what I'm going to now do is go beyond Aristotle to the new phase of Greek civilization, which took place in Egypt almost, in Alexandria. Okay? Athens actually as a culture broke apart, and the Greek culture lived on, and it lived on in Alexandria. So the center of the culture shifted away from Athens to this wonderful city, and that city became the center of intellectual activity. It was founded by this military genius, Alexander. He conquered all the way to India and all the way in Europe, etc. And he, by the way, was tutored as a youth by Aristotle, and so he promoted some of Aristotle's thinking and his ideas. But more importantly, the kings or the Ptolemies that came after Alexander absorbed this philosophy that one should spread knowledge, one should have universities, one should collect knowledge, one should keep it together. And they came up with this wonderful library, the Library of Alexandria. So here's a question based on your reading. It's an easy question. How did the Library of Alexandria acquire this collection of nearly 1 million books? Actually, it was 500,000 books. Okay, we're done. And the correct answer is they had a printing press, right? No. But what is it? B, they copied the work of many cultures and collected them. All right, good. So the intellectuals of Alexandria, who we're going to focus on, they made advances in many fields. And here again, I go back to a detail from the School of Athens by Raphael, where he shows Euclid trying to explain geometry to these students in the School of Athens. And you can see from this picture that one of these guys gets it, and he kind of jumps in excitement when he gets the proof, and this guy is trying to explain the proof to the other guy, and so on. So in mathematics, we had a lot of progress from individuals like Euclid, Archimedes, Apollonius, Hypatia. Hypatia was a woman mathematician and scientist who we'll talk about a little bit. And one of the major advances that took place that I'm going to talk about now is the size of the Earth. And that was achieved by Eratosthenes, who, by the way, was a librarian at Alexandria, at the Library of Alexandria. Okay. And then a major advance in mathematics and mechanics took place by Archimedes, and then fluids by Hero, and so on. And astronomy, this will be chapter 5 and 6, were Ptolemy and Apollonius, and so on. So we'll come back later to that. So I want to talk about Euclid. Euclid wrote this wonderful book which you all use in high school, and his book has the proof of Pythagoras' theorem and many other wonderful things. It's called The Elements of Geometry, and in fact it is really the most widely printed book in the world today, right after the Bible, and very advanced in its thinking for the time. Okay? So I'm going to introduce now, I introduce ideas of reason and theory and symmetry, and I'm going to introduce a new idea that's important for the advancement of science. And that idea is connected, of course, to observation. But it's not just observation, it's measurement. Okay? So it's a very advanced form of observation. And this achievement was made by Eratosthenes, where he figured out the size of the Earth from measurement. I'm going to kind of go through this story a little bit because it's a wonderful story. And if you happen to ever see this video, Cosmos, by Carl Sagan of Cornell, he's passed away, he goes through this in a very, very nice historical way. So that's a nice thing to go to. But the main message that I want you to extract from this story is that it was through close attention to details and measurements where he discovered this way to determine the size of the Earth. So what was the close attention to details? Well, he was a librarian, right? And he went through all sorts of documents in the library, and he read them. He didn't just file them. And one document that he discovered was extremely curious to him. And the account in that document said that what happens, it said that at noon, on the day of the summer solstice, does anybody know what the day of the summer solstice is in the calendar? Good, June 21st. It's the longest day of the year. On June 21st, the day of the summer solstice, there is a strange phenomenon. Okay? And this strange phenomenon is really a paradox, which we'll talk about. And the strange phenomenon is the following. It said, and we'll come back to how paradox leads to this new vision that we'll talk about. Now, what you would expect was that the shadow in Alexandria, where Eratosthenes was, and the shadow in this place from Syene, which by the way today is Aswan, the shadows between these two places will be the same at the same time. Okay, they will be a certain length. But this report in this book said that at noon on the day of the summer solstice, there is no shadow in Sain. Okay, no shadow in Sain. So when he read this, he said, that can't be. He waited for June 21st, he waited for the summer solstice, right? And he went out, he put a stick in the ground. Now he was in Alexandria. Okay? Put a stick in the ground and he saw a shadow. He says, wait a minute, now why is the Sain guy saying there's no shadow on this day when I perfectly see a shadow? See, the Sain guy says there's no shadow, and in Alexandria he observes a shadow. So if the rays of the sun are parallel and the sticks are parallel, there should be a shadow by similar triangles. And then he remembered that Pythagoras and Aristotle had shown that the earth is not flat. Okay? The earth is round. And since the earth is round, it is possible for parallel rays of light of the sun to come and form a shadow on a stick in one place, but at another place which would be directly below the sun, okay, at the time of the summer solstice, there would be no shadow. Okay? Actually, the way that the Sain people discovered this is that they came up with this wonderful event where exactly at noon, at the day of the summer solstice, you could see the image of the sun at the bottom of a deep well. Okay? That means that if you put a stick in the ground, there's no shadow, okay, because the sun is directly over the stick. Right? That's really was the observation. But Eratosthenes figured out that what it means is that the gnomon would have no shadow. And now, this is what we call by paying attention to details. Okay? Most people would just say, oh, well, those curious guys, and go on. But Eratosthenes, he stopped. And he says, why is this? Well, he knew that the earth was circular. And so he drew a stick in the ground at Alexandria. And he drew a stick in the ground at Sain. And he extended these sticks to meet at the center of the earth. And he said, if the earth is spherical, then indeed, I can use this to determine how big the earth is. All I need to do is, if I understand that the sun is very, very far away, then the rays of light coming from the sun to both these places are parallel to each other. And of course, he knew a lot of geometry, because the Greeks were advancing in geometry. And he knew that this line from his stick to the center of the earth cuts these two parallel lines. And so now he has alternate angles. And so he can figure out this angle at the center of the earth if he can measure this angle between the sun and the stick. So he took out his measuring instrument, okay, which, as I said, the Greeks had plenty of instruments at the time, and he measured that angle. And he measured that angle between the ray of the sun and the gnomon to be 7 degrees. So then he said, if I could only figure out the distance between Alexandria and Sain, I could figure out that since this angle is 7 degrees, then the angle in the center of the earth must also be 7 degrees, and I can figure out the circumference of the earth. And I'll show you how. But first he needs to know this distance. So what he did was he hired a troop of soldiers that marched everywhere and said, okay, I want you to time how long it takes you to march from Alexandria to Sain. And then he knew how fast they march. Again, we're talking about observations and measurements, right? Measurements. And he determined that this distance between Sain and Alexandria was approximately 500 miles. Okay? So now he knows that the angle here is 7 degrees, and he knows from his geometry that he learned in Athens that the angle, if you go all the way around, how big is this angle? 360 degrees. So that means that the ratio of 360 divided by 7 must be, give you the ratio of the circumference of the earth divided by 486. Circumference of the earth divided by 486. And so the circumference of the earth must be 25,000 miles for it to give you the same ratio as 360 over 7. Okay? So therefore the answer is 25,000 miles is the circumference of the earth. Excellent calculation. Okay? And in fact, it was the first time that somebody actually explained why the earth looks flat, but it's really round. Because the curvature of the earth is very, very shallow. Okay? If it's 500 miles from Alexandria to Sain, no wonder you don't see any curvature. Okay? Because if you were in a small earth, you would see the curvature. But because the earth is so big, you don't see the curvature. So that's why the earth appears flat to us humans who are 1 or 2 meters big. Okay? Now, I want to, again, make a connection to the cultural thinking of the time. Okay? The cultural thinking of the time had already advanced from the early Greek Platonic thinking of stressing idealization to realism. By realism, I mean really, what's the angle? What's the distance? Okay? What's the shadow? These are all realistic questions. And if you look at the art of Greek at the time, you will see that the narrow focus of abstract idealism, in fact, had broadened already to include detailed features of the real world. So if you look at some of the Greek vases of the idealistic time, you see they're not interested too much in the details of the faces and so on. But as you get closer to the realistic period, where the time that Eratosthenes lived and even beyond, you see the athlete shown over here, showing this discus, this famous work called the Discobolus. He shows in this work the stretching of the muscles, and the motion is ready. Okay, he's ready to throw this discus, and you can see that potential energy in his body in the way he's sculpted the muscles. So he was interested in tremendous details here as compared to this ideal noble athlete of the Greek times. Or look further at this another Discobolus sculpture who goes even further into the details. Or this guy Hermes, who's holding a bunch of grapes, and the famous story is that he's holding Dionysus in his other hand. And in fact, these grapes are so realistic that Dionysus wants to reach out and grab them. Of course, somebody has cut off his hand and the grapes are gone. All right? So anyway, I just want to emphasize the importance of this transformation from idealism to realism. Okay? Now we'll see some of this more in our second scientist that we're going to look at, who is Archimedes. And as before, I tend to talk first a little bit about mathematics accomplishments of scientists, and then go to the science, just to give you a feel for the power of the intellect. So I'm going to give you again some idea of the mathematical accomplishment of Archimedes, and then his physics. So his mathematical accomplishment was he was the first to figure out an accurate value of pi, and more important than that, a method to make it as accurate as you like. Okay, that's really the important thing. So the history of pi is kind of interesting. It occurs everywhere in literature. In fact, in the Bible, in Kings chapter 7, verse 3, it says, "And then he made a molten sea 10 cubits from one brim to the other, diameter. It was round about, and a line of 30 cubits did compass it round about." Okay, so 30 cubits, 10. 3 divided by 10 is pi. Pi is 3 in the Bible. Okay? So their value of pi was approximately 3. And then there were the Egyptians whose formula I gave you. They had this value, Babylonian formula, and India, they had the root of 10. Okay? And the value of pi to so many decimal places is this number. So what is, first of all, just to review, what is pi? Okay? Archimedes figured out pi very accurately. So let me just talk about pi a little bit. So what is pi? Well, pi is a wonderful, wonderful quantity. Take a circle, any circle, a small one or a large one, as long as it's a perfect circle. Measure its circumference by putting a thread around it, and measure its diameter. The ratio of those two numbers is one number called pi. Pi is the ratio of the perimeter of the circle to the diameter. That's what pi is. Okay? And to figure that out in the general sense is what Archimedes did. Okay? And then from there, of course, once he knew what pi was, the circumference is 2 pi times r, okay? Because 2r is if r is the radius, 2r is the diameter. So it's really pi times the diameter, which is the same as this formula here. And he went the next step to figure out that the area of a circle is pi r squared. So let me show you his method. I'm not going to actually work it out. I'll let you work it out in section. But I'll show you the method. He said, suppose you have a circle. I want to figure out the perimeter of the circle if I know the radius. So what I'm going to do is I'm going to just draw a square inside the circle, and I'm going to draw a square outside the circle. Then, by simple geometry, that this distance is r, or this distance is r, I will figure out the perimeter of this square from Pythagoras' theorem, and I'll figure out the perimeter of this square from Pythagoras' theorem, and I'll average the two, because the perimeter in there is in between the small and the big squares. All right, so that's what he did. Then, so if he knew what r was, he could figure this out. And on the next slide, I'll show you the math, but I won't go through it. Okay, but then he said, you know, a square is an approximation to really the perimeter. What I really should do is take a pentagon. So now he needed more advanced geometry. Okay, a pentagon inside and a pentagon outside, and average it, and he got a better answer for pi. And then he said, well, I can do even better if I take an 8-sided figure. And I can do even better if I take a 12-sided figure, which is what he did. And every time if your figures approach the circle, the closer your average will come to the value of pi. Okay? So he figured out a very accurate value of pi and a method to get better. Okay, that's really, really a big step. Now, pi r squared is the area of the circle is really, really easy now. Okay? So what you do is you take a circle and you make pies out of it. Okay? What I mean is like pizza pies. Okay? With these diameter lines. Now you take one of these triangles, all right? If your pizza pie is cut down really, really, really fine, okay? In other words, if this pie was really small, you'd still be hungry, but anyway, if this pie was really small, the area of this triangle is 1/2 the base times the height, which is the radius. Okay? And if it's really small. And all I have to do is sum up all of these triangles. So that means I have to say that the area of the circle is 1/2 the circumference, because that's the sum of all the bases, okay, times the radius. And the circumference I just figured out is 2 pi r. So the area of a circle is 1/2 times 2 pi r times r. So half and half go away, I get pi r squared. That's how you get pi r squared. So very famous proofs. This, by the way, is that first approximation that I'm not going to go through. But the answer is, from this first approximation, 3.414. Looks damn good, but it's wrong. It's 3.141, okay? It's correct. The closer value is 3.141. In fact, the value of pi to many, many decimal places is that. Okay, and you can still go on. Okay, you can still go on beyond that. In fact, if you have nothing to do, you can sit down with one of these two formulas and just keep calculating more and more decimal places for the value of pi. Okay, this is a general formula for the value of pi. You know, you can take 1 minus a third plus a fifth minus a seventh plus a ninth. And the further you go, the closer you come to pi. Or, if you really want to torture yourself, you can take this formula from the great Indian mathematician Ramanujan and use that to figure out pi. Much more complicated. But anyway, I just want to show you Archimedes' cleverness. Now, coming back to physics, okay? By the way, actually, before I go to physics, I want to also point out that Archimedes figured out that you can have, besides straight lines and circles, you can have other geometric figures that have a mathematical explanation and a simple mathematical description. And the first figure that he figured out was this ball trajectory, you know, namely the parabola. Unfortunately, he didn't make the connection that this nice parabola, whose mathematics he figured out to be y equals constant times x squared, he didn't figure out that this parabola is the fountain. Okay, is the path of the fountain. He didn't figure that out. In fact, it's kind of ironical. You know, if you go to Syracuse, where Archimedes lived, there's a center of town in Syracuse, yeah? And in the center of town, there's this wonderful fountain, okay, showing the beautiful parabolas of Archimedes. But he didn't make the connection. Okay? But he did discover the formula for that. Now, let me go to his physics discovery, which is kind of very interesting. Now, like Eratosthenes, Archimedes was very interested in details. And from the details, he figured out new behavior. And the wonderful story about it is his friend, the king of Syracuse, had been given a crown. He had given the jeweler some gold and told the jeweler to make him a crown. And the jeweler had made him a crown. And then the rumor was going around town that the jeweler had cheated the king and had diluted the gold with some silver, because it looked pretty shiny anyway. And the king was a bit mad, and he called in Archimedes and says, "You're a clever guy. Tell me, is this crown really gold, or is it not gold?" And Archimedes thought about this a lot, besides thinking about how to figure out the value of pi. And one day, while he was dunking himself in a tub of water, he realized how to solve the problem. And of course, he became very excited, and he ran out of his bath naked through the streets of Syracuse, shouting, "Eureka!" Right? So that's what we call today the Eureka moment. All right? So if you have a sudden epiphany of some kind, some great discovery, you can call it Eureka moment. But you don't need to run around naked, okay? So that was the question. Is my crown made out of gold? So here was his eureka moment. What he said was, to do it is very simple. I'm going to take the crown, and I'm going to prepare a chunk of gold which has the same weight as the crown. Now, the cultures of Egypt and Babylon and Greece and all were very familiar how to weigh things, okay, so that they could sell in markets, meat and other things. So weighing was very well known. So he just used the technology of the time to prepare a piece of gold, which the king gave him, to make it the exact same weight as the weight of the crown. And then came his inspiration of the bathtub. Okay, he said, let me take a tub of water and mark the level with a pen, okay, and then sink the crown in the tub and mark how much the level goes up, okay, when the crown is in the tub. So this is the increase in the displaced water. And then let me do the same thing with this piece of gold that is the same weight as the crown, and let me see what's the increase in the level of the water when I put the gold in. So what was the conclusion that he reached from this experiment? Was the crown diluted or not diluted? Okay, why? Why do you say it's diluted? It's correct. The answer is correct. But why? Okay, what do you observe? This volume is smaller than this volume, right? And what's happening is when he puts the object in, the object is displacing its volume. So the volume of the crown is bigger than the volume of the gold. Okay, and now come to the concept that you may have learned in high school of density, right? If they were the same material, the displacement should be the same. But it's not the same material. This material is actually a bit, occupies more space for the same weight, okay? And therefore it's less dense. It's less dense. And that's the idea that Archimedes figured out by measuring details like this, okay? And there again, I want to show you that Archimedes came from the same culture. And the details were measure the weights, measure the volumes, check the heights of water displaced, and from that figure out that the density of an object is the weight over the volume. All right. Now, the density of different substances that you are going to work with span a large range. Okay. So if we say that the density of water is defined to be 1, well, actually, you can say that if I take in the units that I'm normally working with, like kilograms and meters, if I take a meter of water, if I take a meter square and I make it into a cube, and I fill that entire cube with water, well, that cube will weigh 1,000 kilograms. So the density of water is 1,000 kilograms per cubic meter. But now look at the density of gold compared to the density of water. The density of gold is 20,000 kilograms per cubic meter, okay? And so on. So now remember that you have to, when you're working out problems relating to density, you need to be careful about the units. So if you use units like grams per cubic centimeter, you have to know how to convert from one set of units to another. And there's famous stories about people who use the wrong units. Yeah, the space shuttle, not the space shuttle, but yeah, actually one of the space rockets in NASA, says, fill me up with fuel, and the guy fills him up with fuel, and he puts the wrong amount of fuel because he's filling him up in gallons, and the guy said, I want so many liters, and as a result of that, they launch this wonderful satellite with a probe to Mars, and they run out of fuel, and they're lost in space, okay, because he used the wrong units to fill up his tank. But that's a very simplified version of the story. But that's really what happened to one of the space probes of Mars, is that they messed up on the units. Especially if you're a pilot flying an airline, make sure you got the right fuel in gallons. All right, so you'll discuss these things in section, okay? Now, I'm going to do this experiment here, and I want you to be able to predict the result of this experiment, and then we'll explain it next time because we don't have the full amount of time left. Where's my scale? Here's my scale, okay? The experiment is as follows, and it's a extrapolation of Archimedes' principle. I'm going to take a chunk of aluminum, okay? I'm going to take a chunk of aluminum that weighs so much, all right? And the question for you is, suppose I take this aluminum block and I weigh it in air, which you're looking at, and then I weigh it, what did I say? I then weigh it in water. In other words, I'm going to stick this, I won't do it yet, okay? I'm going to stick this in the water, all right? So the question for you is, if I do that, what will be the results of the weight when I put this aluminum in water, right? If I suspend the aluminum in water, what will be the result? Okay, I guess I didn't get to question 5, but so for my answer, I'll actually just do the experiment. So we'll see what you got. Display. Wow, you say it weighs less than an air. So let's do it, okay? Then you can go. All right, so it weighs in newtons, 7 newtons, right? So when I put it in water without touching the bottom, it weighs 5 newtons. So the answer is correct. The harder question is what if I did that with steel? Okay, so think about that when you're at home.